Hello everyone, welcome to Basic ICT. Today we will learn about technology. Let's begin our journey together. Before we begin, let's look at today's learning outcomes. You will be able to define information and communication technology, explain applications. Let's get started.
A single data point provides a snapshot, but as that network expands to billions of nodes, it requires a specific architecture to manage the flow. Information Communication and Technology, or ICT, is often simplified to the devices in our pockets. However, the technical definition is broader. ICT refers to the specialized systems used to handle telecommunications, broadcast media, audiovisual processing, and network-based control functions. The current landscape is defined by the convergence of two distinct forces. The first is the proliferation of connected sensory hardware, known as the Internet of Things. The second is the automated processing software required to parse that data, artificial intelligence and machine learning. We are mapping the architecture of this stack, moving from the physical hardware layer up to the autonomous software layer. Tracing this pipeline from physical data collection to automated action reveals the mechanical logic of how current technology operates. The base of this tech stack is the Internet of Things, or IoT. IoT serves as the sensory foundation, linking industrial machines and consumer items via sensors to share data over a network. This concept was visible in the early 2000s, with attempts like this LG digital refrigerator that integrated a screen into a standard appliance. While the idea of smart objects existed in the 1980s, hardware was a primary bottleneck. Computer chips were too large to be embedded into everyday items. These early devices also lacked a unified communication standard and network infrastructure to sustain billions of simultaneous connections. The catalyst that solved this addressing bottleneck was the creation of the IPv6 system. By expanding the pool of available Internet addresses, IPv6 allowed billions of distinct individual devices to exist on the network at the same time. This expansion enabled a scale where Internet-connected devices are projected to exceed 75 billion by 2025.
These nodes include smart home thermostats, wearable health monitors tracking vital signs, and cars receiving remote software updates. Through the adoption of IPv6, the IoT converted the physical world into a real-time data-generating network. However, generating data is only half the process. The challenge shifts to analysis. The data density from 75 billion devices exceeds human processing limits. Manual analysis of this volume is not a viable option. This requires artificial intelligence to serve as the cognitive layer. AI is a broad classification for any system designed to perform tasks like decision-making, problem-solving, and learning. A specific functional subset of this field is machine learning, or ML. Machine learning enables computers to learn directly from data to improve their performance, rather than relying on explicit programming. Nested within machine learning is the even more specialized field of deep learning. Deep learning uses multi-layered neural networks to process information in complex stages. This multi-layered approach is what allows for advanced applications like computer vision and natural language processing. While AI is the theoretical goal, machine learning and deep learning provide the mechanical engines that drive network automation. To understand how these engines parse IoT data, we have to look at the three primary training methodologies. The first framework is supervised learning. This method relies on labeled data, where the algorithm is provided with specific input-output pairs to establish a pattern of correct answers. This is the mechanism used for email spam detection. The system learns to identify unwanted messages based on millions of previously labeled examples. The second framework is unsupervised learning. In this model, the system processes unlabeled data and must identify its own patterns or groupings without a predefined answer key. Its primary function is clustering and finding hidden associations in vast datasets. E-commerce platforms use this to discover customer segments based on purchasing habits that aren't immediately obvious. The third framework is reinforcement learning. This operates through environmental interaction, using a feedback loop of mathematical rewards and penalties to maximize a specific outcome over time. This trial-and-error approach is how a game AI masters chess through millions of simulated matches. These three methodologies determine how raw physical data is mathematically converted into autonomous action. Reassembling these layers reveals a continuous loop. Hardware feeds data to software, which then issues commands back to the hardware. The IoT layer provides constant physical monitoring, and the machine learning layer ingests that data to optimize processes in real time. This integration allows industries to achieve 24/7 automation and a level of diagnostic precision that reduces routine human error. However, moving from manual ICT systems to this automated stack creates specific systemic risks. Because the loop can operate without human intervention, it can lead to job displacement in sectors where routine monitoring and decision-making are now handled by algorithms. Ethical risks also emerge from the training data itself. If the supervised learning models we discussed are fed biased or skewed labels, the resulting algorithm will mathematically amplify those biases in its automated decisions. Transparency is a further challenge. Because deep learning involves hundreds of hidden neural layers weighing variables, the exact logic behind an automated decision is often unreachable for human auditors. Maintaining these systems also requires significant capital, with high costs associated with developing, updating, and powering the dual-layer infrastructure. Finally, by using IPv6 to create 75 billion entry points, we have drastically expanded the attack surface for cyber threats, making the entire network more vulnerable to breaches. The challenge in this integrated ICT landscape is no longer the engineering required to connect devices, but the governance required to manage the autonomous networks they form.
On completing Topic 2, we explored how ICT is transforming our world. Until next time, goodbye, and see you in the next class.